Hello everyone, welcome to our online class on power system analysis. The first topic that we're going to discuss is about system modeling. Now we need to model our network components like synchronous generators, transformers, transmission lines, synchronous motors, in order that we can analyze their behavior, as they are part of a network. So the first equipment that we are going to consider is the synchronous generator. So our synchronous generator is a three-phase machine. So we can consider the analysis on a per phase basis. So that's why we have phase A here, where we have generated voltage of phase A, and we call that as E sub A. And then this is in series with the armature reactance XER, and in the leakage reactance of the winding XL, where XER here is due to the armature reaction. The tendency of the armature current is to produce its own voltage when the conductors cut flux, due to the flux produced by the current. So this has an effect which tend to reduce the voltage generated by our generator. So the reactance drop here, we'll consider that voltage drop, due to armature reaction. So the XAR and the XL are in series, and they can be combined into what we call as XS, and we call this as the synchronous reactance of our generator. And then the windings also has a resistance. So we have RA, and then we have the terminals here. Okay, this is terminal A, and this is of course the neutral. So we have terminal voltage V sub T here. Okay, per phase, and then when load is connected here, so current IA will flow. So that is our circuit representation of our synchronous generator. In other words, we can combine this. We have only XS and RA, in series with the generated voltage. XER, as we have said, is armature reactance, and XL is the armature leakage reactance, and XS is equal to XER plus XL. RA is the armature resistance, and E sub A is the generated voltage of the phase A at no load, and then ER, if we want to if you want to get the voltage after deducting the armature reaction, then it's equal to ER. So we have that. And so therefore our equation governing the equivalent circuit of our generator is that the terminal voltage would be equal to the generated voltage per phase minus the armature reactance drop, minus the leakage reactance drop, minus the resistance drop. So these two can be combined together because we have GIA common, factoring that out. So we have XAR plus XL with the same terms here. And these two, since XER and X plus XL is just equal to X sub E, so we just have this. So with IA common, so we factor that out. So finally, our V sub T is equal to E sub A minus IA, times RA plus GXS. Now, if we look at the phasor diagram, how these voltages and currents uh, represented, in a phasor diagram, meaning we consider their directions. At unity power factor, meaning our current is in phase with the voltage. When the load is resistive, so we have unity power factor angle here equal to 0, and the cosine of that is equal to 1. So that's why we have unity power factor. So for the voltage, we add to the terminal voltage the resistance drop, which is in the same direction as the current, because this should be in phase, and the reactance drop would be 90 degrees, from IRA because of this J. So Therefore, the sum of B sub T, the resistance drop and the reactance drop will be our generated voltage E sub A. Now, take note that the generator voltage E sub A forms a certain angle with IA because we have the same current flowing. So, the generator therefore has its own power factor angle. Okay, different from the power factor of the load, which is the angle between VT and IA. Now, if the power factor of the load is lagging, our phasor diagram looks like this with the current, lagging the terminal voltage B sub T by an angle of theta, and the resistance drop is parallel to IA, and the reactance drop is perpendicular to IA, the resistance drop. And so therefore our E sub A would be this. So again, this theta here is the power factor of the load, and the generator has its own power factor. Now, if we find this angle between E sub A and this current IA, so this angle here, so will be the power factor angle of the generator. So it's different from the power factor of the load. Now, next is the model for our synchronous motor. Now, our synchronous motor is very similar in construction with our AC generator. Now, so except that its operation is reverse. Our synchronous motor draws power from the source, from these terminals with voltage B sub T, and this current will flow to our synchronous motor. Now, as the motor rotates, its armature winding will also produce current, which in effect produces its own flux and develop its own voltage, and we call that as the the counter EMF of the synchronous motor. So we call this as E sub EM. And of course, the winding of our synchronous motors has also resistance RA and reactance XSM. So the equation for our synchronous motor then with XSM equal to XER plus XL. So the terminal voltage B sub T will just be equal to the impedance drop. Now IA times RA plus GXM plus E sub EM. Now, our synchronous motor can be operated with lagging power factor when its field winding is under-excited, meaning the field current that flows in the field winding is below normal. So, it will draw lagging current or lagging power factor. However, our synchronous motor can also be over-excited by increasing its field current above normal, and then in that case our synchronous motor will draw leading current or power factor. Now usually our synchronous motor will be operated in this state, with overexcited field winding, because it will produce leading power factor. Besides from driving a load as its main function, and because it draws leading current, in effect it will improve the power system of the power factor of the system as a whole. So that's the advantage of a synchronous motor over induction motors, where induction motors always draw lagging current. But for the synchronous motors, they can draw leading current, which can improve the power factor of the system, and at the same time drives alone. So our synchronous generator can do two functions at the same time. Now when we look at its phasor diagram, we have the terminal voltage here and the current. So the power factor of the motor as a whole will be taken as the cosine of the angle between B sub T and IA. And then we let our E sub EM as our reference, and then we add to that the resistance drop, which should be parallel to IA, and then the reactance drop, which is perpendicular to this. And adding these three voltages, Okay, the resultant is our terminal voltage V sub T. Next, we go to the model for our two-winding transformers. Okay, we learned from our AC machines that our two-winding transformer, single phase, okay, consists of the primary winding and secondary winding, and so we have here two electrical circuits that are separate. No, they are not electrically connected. Okay, the primary winding okay has NP number of turns, and when we impress okay voltage to the primary winding, then okay current will start to flow, and it produces okay the induced voltage is sub P here, and then the flux that is produced in the primary also couples the secondary winding, meaning they pass through the secondary windings. So with that, there is an induced voltage at the secondary circuit is sub S, okay, for a given number of secondary turns. And so if at the terminals there is also available voltage V sub S, and when we connect a load here, then secondary current okay will flow. Now the transformers are always associated with a change in voltage. It's very seldom that we have transformers with the same voltage at the primary and at the secondary. Usually there is okay, a difference, either that the secondary voltage is lower or the secondary voltage is higher. When the secondary voltage here is lower, and then the primary, then we have a step down transformer. But if the voltage here is higher okay than the primary voltage, then the transformer is a step up transformer. So this voltage transformation is defined by the transformation ratio A, defined as the ratio of NP to NS, or this is just equal to EP over ES. Now for transformers also, it should be the okay the primary field strength, no, which is the ampere turns IP times NP, should equal to the field strength of the secondary, okay, or ampere turns in the secondary, which is IS min S. Now if we divide both sides by NS, then this NS will just transfer here down, and if we divide the equation by IP, then this IP will just be down here. So at the left we have NP over NS, while at the right we have IS over IP. So therefore our transformation ratio also, because it is equal to NP over NS, can also be defined as IS over IP. It is not written here. Now, so for the two separate circuits of our okay, two-winding transformer, it would be difficult okay, to analyze okay, its behavior or performance okay, using two different circuits. So we want to combine okay, the primary and the secondary circuits, and there is a way of combining this. Okay, so first we have to write okay the equation at the primary, which is BP times the impedance drop here okay plus E sub P. So that is our equation for the primary, and for the secondary we have E sub S, and then the impedance drop here okay, then plus the terminal voltage V sub S. So what we can do is that we modify okay the secondary circuit by changing its voltage level to equal to the voltage level at the primary, no? Assuming that this is step down, so it has lower voltage. So we want to increase the voltage in this circuit to equal to the voltage at the primary. So what we can do is we have to multiply this voltage here by A, and this terminal voltage also by A, and we divide okay the current by A and multiply this impedances okay by, now we multiply this by A squared. So the resulting network then would be like this. Now then the same primary circuit, and then for the secondary we have uh, A is sub S here now, and so this voltage is equal to this voltage, no, by definition of A. Okay, so Now the transformation ratio here is 1:1, meaning the same voltage at the primary and the same voltage at the secondary. And the terminal voltage here is also A B sub S. The current is over A, and the impedances here are multiplied by A squared. So when you apply Kirchhoff's voltage law here, we have A E sub S, and then we have the impedance drop here, which is I S over A times the impedance, and then plus this terminal voltage ABS. Now when we simplify by dividing by A, so dividing the whole equation by A, so A would just cancel here, so we have E sub S left here, and then at the right side when you divide this by A, we have also A will also cancel, so we just have B sub S. Now for this term, when we divide this by A, so we have A squared down here. And when we distribute this inside, so this A squared here will just cancel with the A squared up here. So the resulting equation would just be this. Now notice that the resulting equation is the same as equation that we have in the original two-winding circuit. No? So meaning raising the voltage level at the secondary does not alter the performance of the transformer. So it has no effect whatsoever, because the results for the voltages or the currents are just the same. So with that, with the same voltage now at the primary and the same voltage at the secondary, these two ends are now at the same potential, and also these two ends of the windings are at the same potential. Now by circuit theory, that if we have two points in a circuit, two different points in a circuit that have the same potential, we can connect a jumper, a wire, to these two points having the same potential together without affecting the circuit. So meaning we can combine this by connecting a jumper, and we have a jumper. So then these two circuits are now electrically connected by these jumpers. So this one represents our ideal transformer, where we just have the windings and the induced voltages. Now the resistance and the reactances are already separated. So what remains then in our transformer is just the magnetizing circuit, where we have here two components in parallel. One is represented by G and the other one is represented by B. Now G here represents and is responsible for the heating of the transformer core. It is because of the hysteresis loss in the iron laminations due to the changing of the direction of the magnetic flux 60 cycles per second, so there will be 60 changes per second, and the magnetic particles in the iron would collide as the direction of the magnetic flux reverses. And then also we have the eddy current loss because of the flow of flux in the iron laminations. Small circulating currents will flow in the iron laminations, and as these small currents circulating, they encounter the resistance of the plates, and so therefore it produces heating. So these two are responsible for the heating of our transformer iron core, and that explains why when our transformer is in operation, just like our chargers, they will heat up because of these losses, which call as the core loss. Now this one just represents a coil. When excitation current flows through it, it will just produce the required flux of the transformer. So these two currents then will sum up to the no load currents. We call this as no load because when there is no load at the secondary, so I is equal to 0, but still the transformer has current flowing from the primary, and this primary current will equal to this no load current, so it will be very small. But when the transformer is loaded, of course, our IPL will increase. Now this no load current is about 2% of the rated currents of our transformers. So for the analysis of our two-winding transformer, there are two approaches. No, one is to neglect this one, and it will make the calculation simpler. But we have to accept the error resulting from our simplified calculations of about 2%. Now, when we consider this, our calculation would be rather difficult, and but our results should be accurate. So that's what we want to decide, whether we have to follow the simple calculation or we have and incur a small percentage of loss, which is acceptable, and then or we can follow the analysis including the magnetizing circuit here, which makes our calculations difficult. So usually engineers prefer to use the easier way, so we neglect this one, and accepting the percent error of about 2% from the results of our calculation. So what happens then, these two impedances are in series. So then we have here the terminal voltage AB sub S and the current I is over A here, and then at the other side we have IP, primary current, and the primary terminal voltage. Now actually IP is just equal to I is over A because only one current can flow through this. So then these two are in series, so we can combine the resistances together and the reactances also together. So the result is this circuit where we have REP and XEP between the two terminals, along the terminals of the transformer, where REP of course is equal to RP plus A squared RS, and XEP here is XP plus A squared XS. Now however, we should include another line here, which is the neutral, which will serve as the return path of the current. So if a current flows here, so there should be a return path to complete the circuit. So this must have a two-port network. So we have there are two terminals at the left side and two terminals at the right side, and our transformer is just the impedance along this, or between these terminals.